The concept of being able to find the area of a region with a curved boundary like this one is to take the limit of approximations of this area as the approximations get better and better and better. Let's see if we can get an idea of how that happens. For our first approximation, we might just draw 4 rectangles and add the areas of these 4 rectangles to approximate this area. And so what we would do in this case, in number 1, is we would add the areas of these 4 rectangles. Each of these rectangles has a width of a quarter. There's 4 rectangles. The total base here is from 0 to 1, so the total base is 1. We divide it into 4 pieces, so each of these rectangles have width a quarter. The height of this first rectangle is the function value when we plug in a quarter. So the first rectangle has area a quarter times f of a quarter. The second rectangle has width a quarter again, but its height is going to be what happens when we plug in a half. The third rectangle will have width a quarter. Its height will be what happens when we plug in f of 3/4. The last rectangle will have width a quarter, and its height will be f of 1. That gives us an approximation of this total area by adding up the areas of 4 rectangles. We can make the approximation better by using 6 rectangles. So here in the second picture, we've used 6 rectangles. And we can add up the area of those 6 rectangles to get a better approximation of the area under this curve. So in number 2, that's this picture, we have the sum of 6 things, which is the area of these 6 rectangles. And we see a pattern. Again, each of the widths is going to be 1/6 because we use 6 rectangles. The interval was 0, 1. We divided it into 6 pieces. So each width is 1/6. And the heights are going to be f of a 6th, that's the first one, f of 2/6, that's the second one, f of 3/6, that's the third one, f of 4/6, f of 5/6, and finally the height of the last rectangle is going to be f of 1. That'll give us a better approximation because we use more rectangles. We can get an even better approximation by using even more rectangles. Here we used 8 rectangles, and we see that we're getting better and better approximation. In this case, we had overestimated by a lot. Here, it was a little bit smaller of an overestimation. Now there's an even tinier overestimation, and the underestimation is getting smaller as well. These rectangles are getting closer and closer to the actual curve, so we're getting a better and better approximation to the curve and a better and better approximation of area. So to find the area of these 8 rectangles, the width of each will be 8. So here in picture number 3, we add up the area of 8 things. And so we have an 1/8 times f of an 1/8, an 1/8 times f of 2/8 for the second rectangle, an 1/8 times f of 3/8 for the third rectangle, and so on, out to the last rectangle, which is an 1/8 times f of 1. The idea is to put in more and more rectangles to increase the number of rectangles and thereby increase the length of our sum. So each time we're going to add on more and more things to the sum. Different widths, the widths are going to be decreasing, and we'll use this pattern that we've developed for the heights by plugging the appropriate x value into the functions to get the heights of each rectangle. And the concept now is that as we take the limit, as the number of rectangles increases to infinity, we'll get the actual area. That's the process that we'll use to actually define what this area is and come up with formulas for it. It's going to take some work. The first thing that we'll need to do is to be able to get a compact notation for writing out a sum like this, because the sums are going to have to get really, really long as we take this limit, because we're going to have to add up a lot of rectangles. So our next project is to get a compact notation for writing down sums.